Hi, welcome back. In this session, I am going to talk about maximum likelihood estimator, which is a technique used for estimating the parameters in logistic regression. Remember, in case of multiple linear regression, we used ordinary least squares to estimate the regression parameters. However, we cannot use ordinary least square to estimate parameters in logistic regression because many of the assumptions in multiple linear regressions are not valid in logistic regression. So, we had to use a different technique. Let us try to understand what is MLE or maximum likelihood estimator. It is simply a statistical procedure for estimating model parameters given a data. So, basically when we have a data set, MLE chooses the values of model parameters that makes the data more likely. So, that is the logic used for estimating the parameters. So, what we have is a likelihood function, which is nothing but a joint probability function, and the MLE procedure chooses the estimator, which are set of unknown parameters beta. In case of logistic regression, that is the regression parameters beta naught, beta 1 and so on, that maximizes the likelihood function of L of beta. Let me go deep into this. Suppose let us say we have observations x1, x2 and so on up to xn, and the distribution is f of x comma theta, where theta is the unknown parameter. So, since we have the observations x1, x2 and so on up to xn, the likelihood function or the joint probability of that is L of theta, which is f of x1, x2 and so on up to xn comma theta. Now, what we have to do is we have to identify the theta which maximizes L of theta, which is called the maximum likelihood estimator. So, let me take a specific example. Suppose let us say somebody tells me that the data follows an exponential distribution, and I also have n observations, which is x1, x2 and so on up to xn. For exponential distribution, the probability density is given by theta times e to the power minus theta x. So, when I have n observations, the likelihood or the joint probability is f of x1 comma theta times f of x2 comma theta and so on up to f of xn comma theta. So, when I substitute the density function, this becomes theta times e to the power minus theta x1 times theta times e to the power minus theta x2 and so on up to theta times e to the power minus theta xn. So, which is theta to the power n times e to the power minus theta summation of I equal to 1 to n xi. So, that is the joint probability. What I had to do is I had to get the first order condition, but the problem is this function theta to the power n times e to the power minus theta summation I equal to 1 to n xi, when I try to find the first order condition, it is difficult to get that. So, what I do is instead of handling the likelihood function directly, I go and take a log likelihood function. So, when I take log likelihood function, I get n times log natural of theta minus theta times summation I equal to 1 to n xi. So, this is easier function to handle. So, when I take the derivative and equate that to 0, I get theta as n over summation of I equal to 1 to n xi, which is 1 over x bar. So, this is the maximum likelihood estimator for estimating the parameter of a exponential distribution. Now, this is the logic of maximum likelihood estimator. Now, let us see how this logic is used in case of logistic regression. For logistic regression, the likelihood function f of yi is given by pi I to the power yi times 1 minus pi I to the power 1 minus yi. So, whenever yi equal to 1, I get pi I, and whenever yi equal to 0, I get 1 minus pi I. So, now given the data set, I take log of that likelihood function, which is product I equal to 1 to n pi I to the power yi times 1 minus pi I to the power 1 minus yi. So, when I substitute the pi I value, remember the pi I is nothing but e to the power z over 1 plus e to the power z. So, when I substitute, I get a functional form and I take log of that likelihood function, and now I had to apply the first order condition or basically take the first derivative and equate that to 0. So, when I do that, I get a complex function like this. Now, the function was much more simpler when we had ordinary least squares, but I end up with a system of nonlinear equations in logistic regression, which are difficult to solve, or basically we may not have complete solution for this set of functions. So, what we do is we use numerical methods to solve the system of equations, and that is how we estimate the parameters in case of a logistic regression.